Hey, and welcome to the last part of Chapter 1, at least in the way that we are viewing them. Chapter 1, Section 4 is about properties of matter, and properties of matter is a review from physical science. Before we get to the properties, they do also mention the two key words, quantitative and qualitative. Quantitative, think of the word quantity, it's the measured amount of something. Qualitative, think of the word quality. So that's kind of, I think of quality as using your five senses. How does it look? How does it taste? How does it feel? Something to that effect. So again, quantitative quantity is a numerical value. Qualitative quality is basically put into words. So there's two types of properties, physical and chemical. So let's look at physical properties and physical changes. A physical property is a property that can be observed without changing the identity of the substance. So we don't actually change the chemical composition of something. So examples include melting and boiling points. In the textbook, they talk about how we can calculate the temperature at which ice melts. So ice will turn into a solid to a liquid, but the composition of that ice and that liquid water is the exact same. It's still H2O. We did not change the elements at all. Other physical properties include color, brittleness, malleability, mass, and density. A physical change is a change to the form of a substance, but not its chemical composition, meaning again, we're not changing the substance into something totally different. So, for example, cutting. If you cut a piece of paper in half, both halves of those papers are still paper. Boiling, freezing, and melting. Okay, doing a phase change does not change the composition of something. Again, if you take water and it's solid ice, and if you melt it, it turns to liquid water, it's still water. And if you boil that and turn it into steam, it's still water. Dissolving is another thing. Dissolving counts as solubility, which is a physical property. When you dissolve sugar in water, you did not make a new substance. The sugar is simply just dissolved in the water. It's hydrated, is a technical word for it. But it's still sugar and it's still water. You did not make a new substance. A chemical property and chemical changes. So chemical properties are properties that is observable in chemical reactions, and it does change identity of one or more reactants. So example could be flammability. How likely is it that something can catch on fire and turn into something else? Reactivity. How likely is it that two chemicals can be next to each other and react to create something new? Oxidation states is basically dealing with turning into ions. Toxicity is another thing. A chemical change is a change that results in the formation of a new chemical substance. So a chemical change is literally when you create something totally new. For example, when you burn something, you create a brand new substance. Uh, think of nails, iron nails, or a bike or a car that sits out in the rain way too long, and then in the hot humidity it starts to rust. That is a chemical change. That steel changed into rust, which is iron 3 oxide. Technically, the iron that's in steel reacted to oxygen and created iron 3 oxide, which is rust. So what are signs of a chemical change? Well, heat can be produced or absorbed, so something can either feel hot or cold, such as starting a fire. There's a color change, sometimes that occurs. And gas production. Think about if you mix vinegar and baking soda. This is a classic chemistry experiment that's done in elementary, like for volcanoes, where they model volcanoes, where they take some baking soda, pour some vinegar, and it starts to release a bunch of gas very, very, very quickly. Carbon dioxide to be exact. So again, a chemical change is when you take a substance and create something totally new, a brand new substance. At the end of chapter 1, section 4, they talk about extensive and intensive properties. Extensive property depends on the amount of matter, such as mass and length. So the more matter you have, the more mass you're going to have, or the more mass you have, the more matter you're going to have. The example they gave is, let's say you have two nuggets of gold. If you put each of those on the scale at the same time, the scale is going to read higher. It's going to have a more mass. Length, same way. They used buses, for example. If you take two buses and put them long ways next to each other, bumper to bumper, and you add up their lengths, it's going to be longer. So extensive depends on how much matter you have, either the more matter or the less matter. So for example, again, I'll go back to mass. If you have a bucket of water and you take some of that water out, there's going to be less mass. An intensive property does not depend on the amount of matter, such as density. So it doesn't matter. For example, water has a density of 1. It doesn't matter if I have a bucket full of water or an ocean full of water. The density of water is still going to be 1. Okay? That does not change. They're not additive. Temperature, same thing. If I have 2 beakers at room temperature, let's just say room temperature is 50 degrees Celsius, or I don't know what that is in Fahrenheit. Let's just say it's roughly 70 degrees Fahrenheit. Okay, 70 degrees Fahrenheit. If I 2 beakers of water, that temperature, if I pour those beakers together, the temperature of the beaker of water is not going to be 140 degrees. Okay, just because both beakers of water are 70 degrees Celsius or 70 degrees Fahrenheit, if I pour them together, the temperature doesn't add up. The temperature stays exactly the same. That's an intensive property. Density does the same thing. So again, extensive properties depend on how much matter there is. Intensive properties do not depend on the amount of matter. And that's it, and we are done.